Okay, so first thing is you write down the problem that you're given. And alright, so we gotta balance this equation. I know that I'm gonna have to put a 2 here because my oxygen only comes in an even number. So then that means I have to put a 2 here, also a 2 there because of my sulfur. So then I count my oxygen. I have 4 and 2, that's 6, so I need a 3 there. And I'm gonna start. So in the problem, it said 8 moles of hydrogen sulfide. How many moles of oxygen gas would be needed to completely burn 8 moles of hydrogen sulfide? So before I have 8, this is my question, and I don't have any product. I haven't done it yet. During the change, we completely burn the 8 moles. So we're going to take that away. And then that will leave us with 0 moles of hydrogen sulfide. But I want you to look. Molar ratio, these are the same. This is a 1-to-1 molar ratio between hydrogen sulfide and sulfur dioxide. It's a 1-to-1 molar ratio between water and hydrogen sulfide. So if I don't want to do that factor label, I can just say I'm going to gain 8 moles of these because of the molar ratio. Okay? Now for oxygen, you might be able to do that in your head, but I'm going to go ahead and do the factor label so we have one more example. If I start with 8 moles of H2S and I perform that molar ratio problem for oxygen, 8 times 3 is 24, divided by 2 is 12. So I'm going to need to use up 12 moles of oxygen. Now, some of you could clearly see that, okay, what times 2 gives me 8? That's 4. So I have to multiply these by 4. If that's where you're at with math, that works. But if you can't see that in your head, use the factor label method. Okay, so then we're not going to have the oxygen, so we've used it up. Now, we don't know. This could be in air. So we could put excess here. It says burns in air, so that would be an excess. And we still have our products of 8 moles of sulfur dioxide and 8 moles of water. Okay. Some of you are going to think that these BCA tables are way easier. Some of you are going to be like, why do we have to do that? It's all about what you can visualize in your head with math and what you have to actually draw out. And everybody's at a different place with that. Let's do number 2. Number 2 says, propane C3H8 burns in air to form carbon dioxide and water. If 12 moles of carbon dioxide are formed, how many moles of propane were burned? Well, first, we need that chemical equation, or that balanced chemical equation. So there's our propane. If it's burning in air, what part of the air is actually doing the burning? Oxygen, that's right. And I can't just put an O because we know oxygen is diatomic. And it forms just a normal combustion reaction, CO2 and water. Well, first thing I see, I have 3 carbons, so I need a 3 there. I have 8 hydrogens, so I need a 4 there. And count up my oxygen. 3 times 2 is 6, 4 times 1 is 4, so 6 and 4 is 10. 2 times 5 gives me the 10 oxygen I need in my reactants. And I'm going to create my BCA table. So I'm going to go ahead and draw my line. and go back to my problem. 12 moles of carbon dioxide are formed. Let's process that. We didn't have any of this product yet. So it's during the reaction that we get 12. Okay. And then it tells me how many moles of propane were burned. Well, I could go through and do factor label for this. Or I could look at my ratio, just look at the ratio. 3 times 4 gives me 12. So it's a 4 times the amount of the coefficient. So then I could just say, well, 4 times 4 is 16. What's 4 times 5? 20. So I had to use 20 moles of oxygen. And if we look at oxygen, it says in the problem it was in air, so oxygen was in excess. Alright, so we did 4 times 4 is 16, 3 times 4 is 12, 5 times 4 is 20, 1 times 4 is... Oh, come on now, 1 times 4 is 4. So we had to use 4 moles of propane, so that means we had to have 4 moles of propane to start with. Okay, and then we go through, okay, 4 minus 4 is 0, excess minus 20 is still excess. We have 12, and we have 16, because we started with none. Okay, and from that we can say how many moles of propane were burned. It was 4. So the BCA table is really important if they give you a problem like this and you're given some amount of product, then you can find all of the amounts that you need. You could also take this then and find out how many grams of propane that you might need. Alright, I'll go ahead and do 3, and that'll give you an even number to go with. Yes, sir. Alright, so let me scroll up and look at 3. Ammonia for fertilizer is produced by causing hydrogen and nitrogen to react at high temperatures and pressure. How many moles of ammonia can be made from 0.15 moles of nitrogen gas? Well, we need a balanced chemical equation. So we know that that ammonia is going to be the product. Hydrogen and nitrogen, what do we know about both of those elements? We know lots of things. Can hydrogen live by itself? Nope, it's diatomic, it's part of the 7. Nitrogen, also diatomic, also part of the 7. So we got 2 and 3, we know we're going to have to get to 6. That gives us our 2 nitrogen, and there's our balanced chemical equation. So then our BCA table. Our problem says how many moles of ammonia can be made from 0.15 moles of nitrogen gas. Okay. Now this one, I love this problem, because if you really have a grasp for this, tell me, why do I love this problem? Because my n has a 1 coefficient. So when I look at my ratio, I'm just going to multiply what I'm given in n times the coefficient. And that's going to give me what all these numbers I need. So in the reaction, I'm going to use up all of this. I'm going to use up 3 times the moles of hydrogen. So I'm going to use up... Okay. And then I'm going to add 2 times the moles of ammonia. So I can just say 2 times 0.15. Now, we gotta fill in all the rest of the spaces now. I started with 0 product. I probably started with excess hydrogen, because it doesn't give us a number. So I'm left with, because 0 plus 0.3 gives me what I'm left with. I'm left with no moles of nitrogen because I used it all up. And then probably excess of hydrogen, since we're not really told. Right. And so our answer would be 0.30 moles of ammonia can be produced. If you want to go ahead and go on your own pace, that's fine. I'm going to go ahead and do 4 on the screen, but I'm going to expect you to have at least 2 more done for your homework for this lesson. Okay, at least 2 more. So I'm going to, like I said, I'm going to go ahead and do 4, but you need to have at least 2 more. So here's 4. 4, the problem says the poison gas phosgene reacts with water in the lungs to form hydrochloric acid and carbon dioxide. That sounds highly deadly. Let's look. We have phosgene with the water to make hydrochloric acid, which we have used, well, not used, we have used in problems before. And we know that's HCl. And carbon dioxide. So this one, if I look carefully, my oxygen is uneven. So I'm going to go ahead and even that up because in my product it's only even. And so I might have to, let's see. I need 2 Cl's here, and I also need 2 hydrogens, so if I put a 2 there, that helps me set that. Okay, need a 2 here. I have 2 carbons, 2 carbons, 2 oxygens, 4 oxygens. So I need a 2 here. Let's see if we got it. 2 times 1 is 2. 2, that gives me 4. That gives me 4 oxygens. I need a 4 here. Because 2 times 2 is 4 hydrogens. 2 times 2 is 4 chlorines. That's the numbers I need. So I could reduce that equation. Let's do that. So we'll go 1, 2, 1, 1. Alright. That's what we'll actually use for our problem. And BCA table. So in the problem, I'm given 0.835 moles of phosgene. And it wants to know how many moles of hydrochloric acid would be formed. So here's my question I'm looking for. Okay, I'm going to totally use up all of my phosgene. That's what the problem says. And so I'm going to be left with 0 of that. Then, let's see. This is a 1-to-1 ratio, so I'm going to use up the same amount of water, and I'm going to come up with the same amount of carbon dioxide. Alright. So water was probably in excess because it said it happens in the lungs, which are moist. If I look at my hydrochloric acid, I had none to begin with. That is a 1-to-2 ratio, so I'm going to have to multiply that by 2 to get 1.67. And so after it's all said and done, I will have 1.67 moles of hydrochloric acid. The same for carbon dioxide. I started out with none of it, and I'm going to get 0 plus 0.835. So then my question said, how many moles of hydrochloric acid would be formed? So I would answer 1.67. So BCA tables really just give us a good representation of what's happening throughout the whole problem. Alright.